Hello and welcome to our next module in the course Introduction to Data Analytics. In this module, we continue our previous work on descriptive statistics, and in our last session we spoke about descriptive statistics through the use of various graphical and visualization techniques. In this module, we start with the use of summary statistics, or the idea that you can describe data with numbers. Numbers that summarize the data. And more specifically, we are going to be talking about measures of central tendency in this lecture. So, just to jog your memories, we spoke about the idea that there could be a data set, and a data set essentially would be representing could potentially be representing a particular variable, and so I've provided for you a simple example of a data set, and this data set is what is being captured in this histogram. The histogram is a visualization tool that we spoke about in our last lecture. Now, the histogram essentially is a very rich representation because it not only captures just some parameters associated with this data set, but it captures various nuances associated with it. So just to give you a quick reminder on how this works, essentially the entire x-axis breaks down possible values that the data set could take. So for instance, this bin is the series of values between 10 and from the looks of it 10.66 on this side. Now, depending on the number of data points that you see here that fall within that range of 10 and 10.66, that would get counted here, and out here it looks like that's about 15 points. So that's essentially how a histogram is calculated, and the idea is that using a histogram you could then fit something called a distribution, and the distribution is this red line that's shown on top of the histogram. And so in some sense the histogram and the distribution that sometimes follows tells us the full story associated with the data, and usually this red line is represented through some kind of a formula, and we just call that, let's say, f of x for now. But the basic idea behind summary statistics is that you don't even need to go this deep. I gave you this full picture just to tell you what the richest or the most detailed story could be, and our next sessions, next modules are going to be about distributions. But now let's take a step back. Is there something simpler that we could do? Is there something simpler without even fitting this distribution or even creating this histogram that could tell us a part of the story? And the answer is yes. And there are these various summary statistics that do exactly that, and I'm just going to talk about a few of them now. The first and the most common one are these measures of central tendency, and what they mean is that you have this data set, and for now let's just occupy ourselves with the histogram, not the distribution that's fitted on top of the histogram, but essentially with this histogram, what is a fairly central value, right? So it's clear that the values of this distribution go from here to about here, but what is something in the center, right? And how do you define that? So one idea is often to say, well, one measure of central tendency is to see the minimum value going all the way to the maximum value and take something that's in between, right? So that's one way. Another way could be to say, at what point in this histogram am I really covering about 50% of the area? So this histogram is defined by these blue bars, and at what point am I covering about 50% of that area? So that could be one way of saying what is central. There are other innovative ways. One of the most common one is to say think of this as a balance, as a seesaw essentially, this x-axis line, and all these blue bars are weights on top of it. So the idea is, where would you want to put a fulcrum such that this whole thing balances, does not uh, tip off, or the seesaw is essentially in balance. So that's the core idea behind measures of central tendency. What is a central value? Um, Now you then have measures of dispersion, and the idea behind measures of dispersion are that, oh, so you might have something that's a central value, but how are your data points actually dispersed around this central value? Are they very far away from them, or are they very close to it, and so on? Um, and these are the two major forms of summary statistics that we will cover in this course and that you are likely to encounter. But you might have also heard of the concepts of skew and kurtosis, and so it's just briefly worth mentioning it. Skew concerns the shape of this distribution itself, and the the fact that sometimes distributions lean to one side versus the other. And this is a fairly colloquial way of saying it. But instead of this distribution, the red line being the way it is, could you have a distribution that looked like that? Which means the whole thing is leaning to one side. Again, I'm just giving you a conceptual feel for it. It's not a formal definition. In the same light, kurtosis is the idea that how fat are the tails of the distribution, and what we mean by that is having a similar distribution that looks like this, right? So the tails themselves are fatter than the other, and that property gets captured with kurtosis. So great. So this should have given you some a brief overview of the overarching idea of summarizing statistics through describing statistics through summary statistics, or numbers as a means of describing distributions. We now go into the major subject of this lecture, which is measures of central tendency. So the best way to do this is through a concrete example, and that's what we will do with this step. So there are three major measures of central tendency, and they are the mean, median, and mode. With the mean, the core idea, and many of these you might have encountered, or you might have come across before. So bear with me if you've already heard this. The idea behind mean is just that it's the concept of average. If you have a data set, and I've just given you a sample data set out here, and so it's the numbers 3, 4, 3, 1, and I've kept the data set small so that I can illustrate the concept. Typically you might be dealing with much larger data sets, but the idea remains the same. So for this data set, the mean is nothing but the sum of all the numbers divided by the total number of numbers there are. So we take each number, 3, 4, 3, and we add them all up, and the 12 that you get out here is the actual number of numbers that there are in this list. So once you divide it, that's the concept of mean, which can also be represented mathematically in this form. And I've just shown that to you so that when you see that, you're not surprised by it. So great. And incidentally, the mean is the concept that I was speaking about in this histogram of balancing the seesaw. Where would you place the fulcrum such that this seesaw gets balanced? That's the same concept of mean. We now move on to the next measure of central tendency, and it's called the median. The median is calculated by arranging all the numbers in order. So you had this data set, and it was 3, 4, 3. That's what you had out here. But when you bring it to a median, you basically take the smallest number, put it first, and then in some order, ascending or descending, you arrange the numbers. Once you do that, you choose the central number, and that's your median. Now choosing that central number is quite easy when you have an odd number of numbers. So if you had 9 numbers, right, the fifth number would be the central number. So you have 4 numbers before and you have 4 numbers afterwards, and that's your central number. But when you have an even number of numbers, right, so in this particular case we have 12 numbers, the central number is really not one number, it's 2 numbers. So out here it winds up being the 6th and the 7th number. So typically there you choose the 6th and the 7th number and take the average. In our particular case that's not a problem because it happens to be the same number, and quite easily we say that the answer is 4. The mode, which is the third measure of central tendency, and there might be a few others, but these are the 3 most common ones that you will encounter. The mode essentially says what is the most common value. Okay, so if you look at this data set, the number 3 appears 3 times. The number 4 appears twice, and then all the other numbers just appear once. And so out here it's fairly clear that the number 3 is the most common one, and hence 3 is the answer. If the question is what is the mode, it's the most common number. But that kind of makes sense, right? If you have a data set where there are only a few numbers that are recurring, but the concept is again generalizable. So even if you had a data set that looked like this, where numbers doesn't make sense to ask the question which is the most common number. In fact, no number might repeat itself. But out here the mode essentially is based on the range itself. So you would say this is the most common range, and so this is the mode. So the mode out here would have been something like if 9.5 or 9.6. I'm just eyeballing it. So great. So we now understand how mean, median, and mode are calculated. Now let's take a step and see where do we want to use which measure of central tendency. So how do you choose between mean, median, and mode? The main contest really comes between mean and median. So let's talk about that for a minute, and it becomes kind of obvious where mode is more useful. Because it has a very different property associated with central tendency. So great. If we had to choose between mean and median, much of the debate usually comes down to outliers. The idea of outliers is that it's a number or a value that's not really within that set of most of the other numbers that you see. Now that can be because of quite a few reasons. When this comes about because of an error in the data, so the data set itself could have an error, then it's easy to say that's erroneous, right? That's a bad outlier. But sometimes the state can be that the outlier is very much not an error, and it tells an important part of the story. In really simple words, the median is not influenced much by the outlier, whereas the mean is greatly influenced by the outlier. For that reason, the median is often kind of expressed as being a more robust metric to outliers. But then we need to take a step back, right? Just a second ago I was saying, outliers can either be good or they need not be good, and so it really depends on what we think about the outlier as to whether we choose to go with the mean or median. Obviously, when we think the outlier is a bad thing, it should not be there, or it's not contributing towards a story that we want to tell, then we call it a bad outlier, and you prefer the median in that case. So to actually give you some insight as to how the outlier affects the mean and not the median, let's just go back to the previous example. Let's say that in our data set, instead of 8, we had 800. Okay, so that's clearly a mistake. Someone by mistake typed 2 zeros next to 8, and so it's 800. Let's assume it's a mistake, it's not obvious. Now, in the case of the median, this would have a huge impact. Instead of 8 being here, you would put in 800, okay, and that would greatly change this number. So your mean is largely affected. It would probably send the number into the hundreds. Now, it will have no impact on the median. This 8 gets listed, it becomes 800, which means that it's not in its place. It comes after 9, so make some space here. So the 800 comes here. Alright, but the central two numbers still remain these two 4s. These two 4s, right? So your answer really did not change. So in many ways, the outlier has like this huge impact on the mean, and it has no impact on the median. Now, clearly, if what you're faced with is this kind of an error, you like using the median, right? Because the mean is susceptible to this problem. There might be other situations where you want to use the median, and again, it pertains to outliers. But here, you're not as much scared about errors, but you are scared that there is this one atypical case which is just skewing the story that I want to tell. So a classic example of where medians are used is when looking at salaries of people, where the idea is that salaries are in some sense exponential. Many people earn a consistent salary, and then there are these few people who just earn these catastrophically high amounts. And so something like mean, and here the idea is that the catastrophically high amounts are these outliers. And here talking about a mean will not give you the typical salary that a person earns, because of these one or two people who earn very high salaries. So it's not just errors. There might be other situations where you have outliers and you feel like the presence of these outliers is moving you away from talking really about what is a typical value. Now, having said that, there are many situations again where you are dealing with outliers, but these outliers are a very important part of the story. So let me give you an example of this. So let's say you had this data set where you were looking at a particular financial strategy, and in this financial strategy you are looking at how much money you made on a daily basis. And so you've taken some historic data, and you want to see what is a typical scenario of the strategy. You want to evaluate the strategy based on this data set, right? So let's say this financial strategy actually made you lose 1 rupee every day on 99% of the days. But on 1% of the days, this strategy gave you 10 crores. So it's a large enough number, right? So this strategy made you lose money on 99% of the days, and on 1% of the days gave you 10 crores, right? Is this a strategy you would like to take? The very straightforward answer is, if you like making money, you really like the strategy, because despite the fact that you lose just 1 rupee on 99% of the days, as long as you can play this game, or you can trade on this strategy in the stock market for a long enough period of time, you're bound to in the long run make a good amount of money, right? Because 10 crores more than compensates for the 99 days during which you lost the 1 rupee. Now let's see how mean and median would have represented this data, right? If you got a sufficiently large enough data set of having actually played the strategy, so let's say you go and you actually collect a data set of the strategy over 1,000 days, or let's say 10,000 days, right? What would be the median of this strategy? The answer is that the median would have been the -1 that the 1 rupee that you lost, right? So quite simply, how is that? On the data set for this would look something like this. It would look like this: -1, -1, -1, comma, dot 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 dot, with a lot of minus ones. 99% of them are minus ones. And then the odd time you're going to find this really large number. I'm not even going to talk about how many zeros, but it's got lots of zeros. Dot 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 for the zeros, right? So you put this in ascending order and you choose the middle value. That's going to be a minus 1. So the median gives you a minus 1. However, you put these numbers, you add all of these numbers up together, right? Put your 10 crores in there with lots of zeros, and then divide it by the total number of data points, which is 1,000 or 10,000 or something, whatever the number of data points you have, and you're going to get a very large positive number. Positive and large with great signs. Okay, so here is a story where, yes, you had an outlier, you got this huge outlier which is 10 crores, but the story was in the outliers. That's as much real money that you made or lost as the 1 rupees that you lost. So here's a case where the mean is probably a great measure to go by if you had to choose whether to play the strategy or not. So I hope that gives you some idea between mean and median. Now let's talk a little bit about mode. Mode is an interesting one because it just blanket says I'm going to take the value which is the most popular, and that works fine for distributions which are fairly symmetric, but in many cases that people don't find that too meaningful. The one big advantage, however, that the mode has is that you can even use it with nominal variables. So you might have a situation where you're just counting the number of you're coming up with a count associated with a categorical variable. An example could be the number of reds, the number of greens, the number of yellows, and all the mode is going to do is say, let's pick the one which has the most number of it. And it can also be fairly useful in multimodal distributions. Let me give you an example of a multimodal distribution, and multimodal just means that there are many peaks to the distribution. So if you go back to this slide, and let me just erase that for you. So the red line is the distribution, and we're going to talk a lot more about distributions. A multimodal distribution is one that might look like this. So there are like 2 peaks for this distribution. Okay, so let me give you an example, a real life example of where you could have a multimodal distribution and where you might want to use the mode. So let's say you lived on this street, and the street was 100 meters long. So one end of the street is 0 meters, and then there are markers on the street. So there's 1 meter, 2 meter, 3 meter, and the street goes all the way to 100 meters. So if someone said the 75th meter, you immediately knew which point of the street or road they were talking about. Okay, great. So all the residents of this street need to make a decision on where to place a garbage can, a trash can, which let's say for whatever reason people have strong opinions of that. So people are all going to vote, or we're going to take a survey of all the residents, and each one's going to come up with a number. So person 1 says, I want the garbage can in the 25th meter mark. Another person says, I want it in the 50th meter mark, and so on and so forth. Now let's say we collected all this data and we found that 40% of the residents said they want the garbage can in the 25th meter mark. Let's say another 40%, or let's say 45%, said they wanted the trash can on the 75th meter mark. So just to recap, 40% of the people say they want the trash can on the 25th meter mark. 45% of the residents say they want it on the 75th meter mark, and the remaining 15% it's all over it's like uniform, somewhere between 0 to 100. Now the problem is both mean and median might wind up saying the average preference is to keep the trash can somewhere in the 51st, 52nd meter mark, right? Because that is bound to be a central value. Now, that might be something that nobody wanted. Whereas something like a mode would just categorically say keep it in the 75th meter because that's the most populous preference. So in cases where kind of taking two extremes and averaging them out, and in some sense median also does that as long as there are enough data points, does not work. And in those cases, the mode could be a fairly useful application. I hope this gives you an idea of the different measures of central tendency. In the next lecture, we will take up measures of dispersion.